Yeah, this is going to be a quick introduction to variable speed rise frequency converters. These are units that can set the speed to an electric motor to pretty much any speed you want. You can even overclock the motor so it can run faster than normal with the standard supply. So they can look something like this. There is a drive unit, a frequency converter of some sort, and a motor. I think this is a servo system from Siemens. They're called Dynamics servo system. So here's just there's a one cable connection for the OCC. PN is Profinet here. So they have a servo system, they have a micro system for small motors, and they have a huge system that can supply a lot of power to large motor. And a little here about how they are designed and constructed. Application, we can use them for moving and so on, conveyor belts, roller conveyors, chain, and so on, which one you can use and how to use it. Here are the types, and these are just what Siemens tells you what they can be used for. And again, more application, machining and processing, which one to use. So this is kind of a selection which Siemens frequency converter to use. Of course, there are other frequency converters. Danfoss, I think, made the first frequency converters. ABB, they have good frequency converters, and there's there are a few, but we are looking at Siemens, just as an example. So this is the frequency converter variable speed drive construction, how it is constructed. So there's a rectifier part, there is a DC link, and then there's an inverter. So we rectified, and based on the DC voltage, we can make pretty much any sinusoid voltage to my three-phase motor. So the DC link is capacitors, and there's a coil inductor here to smooth things too. Okay. There's a microprocessor, microcontroller, very fast one in here. So here's rectified, and this one is then, let's say, switching these switches on off, and they are normally IGBTs because they're really fast. Shuts off power in 400 nanoseconds and turns it back on in 500 nanoseconds, and that's kind of nice when you're going to work really fast with the switches here, on the switches. One problem with frequency converter was to have a microprocessor capable of running fast enough to implement this. So the sequencing of voltages, it depends on how you connect these. Let's say at the start, there's nothing out here. And then you just say, okay, we let the power flow through. This is just for one winding this way. And then we basically just make a positive voltage, but the sinusoid has to go negative too for making this work. So then we just switch to off again, and then we just switch the switches so the supply is in the opposite direction. Yes, that was probably for the B. This one should probably be over here for the A phase, but it's okay. No, it's for one phase. Of course, they go to the A plus to B minus and A minus to B plus, or B plus to A minus. Of course, it has to be like this. So this creates an alternating voltage, which is going to look like something like this if you use pulse width modulation on the IGBTs. And due to smoothing and the capacitor and stuff in the system, what you have, it's going to look something like this. And then you can make the voltage higher and compact it to make the frequency higher and lower. So that's higher voltage depends on how long, let's say if we go back here, is how long do you keep the capacitor switched on to have the inductor, let's say, charge in the system. For how long are you doing that? Yes. The voltage is either fully on or fully off. This is the duration of the pulse that determines how much voltage buildup you can have in your motor, so to speak. Okay, so shorter on time, lower voltage, longer on time, higher voltage, and the frequency, of course, is the spacing between the pulses, how fast the spacing is between the pulses. Okay, and then if we want to break this stuff, we have to transfer some energy back into the DC link, or we have to get rid of the power stored in the motor, or especially the mechanical power stored in what the motor is actually driving. And one way of getting rid of it is use a brake resistors. Just say bleed off the power through a resistor. It's getting hot, so put it somewhere where the heat doesn't do any damage. But then again, the problem here, if the voltage here gets too high, then as a safety measure, the frequency converter shuts down. And that might not be desirable for all applications we use the frequency converter. But then there's another option. Why get rid of the power? Why don't feed it back into my mains and get paid for it, maybe? At least I'm not using power. So I just feed it back into the mains. And then you have two identical systems can work in the same way. So the rectifier is based on IGBTs, so some power electrons you can control. So when you are braking, it's just feeding it back onto the DC link, and the DC link is kept at acceptable levels by this unit feeding the power back into the mains or the line. And of course, this inverter here has to match the frequency on the power lines, which is of course capable of doing. Speed versus torque. Quick, there is a constant torque region, a constant power region, where you have more or less a constant power region. But here you have speed, and also the frequency converter can provide a breakaway torque to just start up the system, just inject some current to get it to move fast. And then it's the control. That's just a quick one. Acceleration through an S-curve, usually use a sigmoid curve type like this. You can be on so it's the max. So this curve is looking like this, and the reason why it's used is that the acceleration or the derivative of the acceleration, which is called jerk, you just kind of jerk on the component you are controlling, is minimized. Probably there is also another formula you can use if you can't implement this one, but modern PLCs, they can handle exponential function, so you can just implement this, and that's what the drive does too. Of course, you don't have to do that because the drive does it, but if you want to have to make a function or speed profile like this, you can do it by using this or implementing this function. This was a quick introduction to frequency converters. We looked a little at the schematics, which is that's the Siemens range of frequency converters, and then looked a little on the principle of how a frequency converter works. A frequency converter is a complicated device with a lot of parameters. It can do pretty much anything you want and not want. They even contain PID controllers. So if you need really fast control, for instance, pressure control on a compressor, pump, or whatever, on a medium, you can put a controller which then has to be fast, at least for non-compressible medium like water, things like that. They have to be really fast if you want to control the pressure, put the controller in the frequency converter. That's an option you have.